Now let's talk about the expectation of a random variable. So by expectation, we are talking about mean, or what we also refers as average. So basically, the expected value of a random variable is considered to be the probability weighted average of the possible outcomes of a random variable. So for example, if we have two outcomes of any event, let it be for a Bernoulli distribution where we have two options of 0 or 1, and the probability for these would be equal, that is 50% into 50%. So basically, by weighted average, we are saying that we will be multiplying these two observations with each other. So if we are trying to calculate average of a Bernoulli distribution, it would be equivalent to 0.5 into 0 plus 0.5 into 1. So basically 50% here and 50% here into 0 and into 1. So if we do that, the answer would be 0.5, because 0.5 into 0 would be 0. We can also represent it through this equation in which expected x is equal to xi into summation of pxi. In this particular case, we'll be using two observations in which we have 0, which is actually the xi, and we have px is equal to 0, which is a probability, which is 0.5 in this particular case. And then we can calculate the px is equal to 1, which is again 0.5 and 1. Having said that, if the weights are equal, then it would be way easier to calculate the average. For example, even if we ignore this 0.5 here, if we want to calculate the average of this, we would just be adding 0 and 1 and divided it by 2. So another method or another formula for calculating the expected value is that we basically add the values, summation of all xi divided by n, the number of observation, and this formula actually assumes that the observations are actually equally weighted. So if observations are equally weighted, we can just add the number and divide it by n. If we don't have any probabilities assigned or probabilities given to it. But if we have different probabilities for different values, we would be using this particular formula to calculate it. Similarly, if we have to calculate the expected value of roll of a die, where x is equal to number that faces up on the die, is calculated as, again, the formula is same. Expected x is equal to summation of pxi into xi. Now here xi ranges from 1 to 6. So basically we'll be calculating expectation for 1, then 2, then 3, then 4, then 5, then 6. For all of these options, the probability or the pxi would remain same, which would be equal to 1 by 6. The answer or the expected x in this particular case would be 3.5. Now you can argue that basically 3.5 is not there in these options. So the x was actually from 1 to 6, but the expected value of 3.5. So basically, if we are calculating long run average, if we are rolling the dice for a large number of time, maybe 1000, 2000 time, and then if we calculate the average, it would come around 3.5. So the number would be between 3 to 4, somewhere around that. So basically that's the median, that's the middle of that particular number. So this is how we calculate the expectation or the average or mean for a dice. But this is a formula to calculate average or expectation for discrete random variable. If we have continuous random variable, the expected value would be a little different, and we will actually be integrating the function of the distribution to be able to come up with the expectation. So expected x would be equal to integration from minus infinity to infinity x into fx dx. We won't be needing to do any integration in this curriculum, but the idea is just to give you heads up on of how we can calculate expectation of a continuous distribution, which would be a little different from what we do for discrete random variable. We'll be talking about the expectation of some continuous distributions in the next chapter. But of course, we won't be calculating it using integration in this FRM curriculum as of now. Now, the expected value has two broad properties. The number one is that if C is a constant, then expected of C into X is equal to C into expected X. It means that basically this constant do not actually impact the expected X. So if the expected X is 10 and if the C is 10, then this equation would be expected 10 into 10 is equal to 10 into expected of 10. So basically these equations would be equal. Similarly, if we have two random variable X and variable Y, then the expected values of these two variables, expected X plus expected Y, would be equal to the expected values of the individual sums of these variables. The mean or expected value of two variables would be sum of their individual expected values. Now let's talk about four common population moments. These moments have a significant contribution to the statistics and probability. Basically, what happens is that all of these functions are actually defined by distributions. We have separate chapters for distributions, for probability distributions. But these distributions are actually defined by four broader population moments. These moments include mean, variance, skewness, and kurtosis. So we just discussed the mean, which is also referred as expectation or average. The average or expectation is also known as the first moment. It is called the first moment, which is defined by the expected value or average. So basically this first moment is equal to expected value of X. How do we calculate it? Very simple. If there are, let's take an example, if there are 45 students in a class and 5 students were randomly selected from this class and their heights were noted in centimeters. Let's suppose that their heights were 131, 148, 139, 142 and 152. If we have to calculate the expected value of X, what we'll do, we'll just sum these numbers and we'll divide by 5. As discussed earlier, basically expected X is equal to summation of X divided by N. So we are just adding up these numbers and dividing by 5. So the number or the average would be 142.5 centimeter. So what advantage do we have to calculate this mean? Basically, we did not have to calculate the height of 45 students, which is considered as the population. We just took a sample of 5 students. We calculate the height of these students and we took an average. And based on this sample, based on an average, we can say that, the average height in this particular class is about 142.4 centimeter. Why? Because ranging from 131 to 152. So we will have people around 142, which would be the most number in terms of height in this particular class. So using this first moment, we can have some idea about distribution, that what sort of expectation should we have about a particular indicator. In this particular case, we have height. The same can be applied to the marks or weight or any other indicator. Now the second moment is known as variance. So mean gives an idea what sort of expectation should we have about the average value. Variance tells us that what is the variation. So for example, 142 is the average, but what is the variance like? How the other values are different from 142. So basically, variance is the second moment through which we try to calculate the variation around mean. variation around mean. So basically we want to calculate the dispersion of the distribution. So is it actually ranging from 131 to 152? Or most of the observations are actually between 137 or 145. We want to calculate it. We want to have an idea about dispersion using this variance. So the formula of variance is sigma squared is equal to expected x minus expected x squared to the power 2. So basically what we do is first we calculate the average of this particular distribution. For example, here we have 5 distributions: 131, 148, 139, 142 and 152. This is our x. Based on this we calculated the average. We already calculated, it came out to be 142.4 centimeter. To calculate the variance, now we will take the differential of these two. So x minus mu will be calculated here. So whatever these numbers are, then based on these numbers we will calculate x minus mu whole square. Okay. So this is something that we have done here in this particular equation. So we will actually subtract the individual number from this mean everywhere, and whatever the number is which can be generated here, we'll just square it. We will just take a power of it, and then in the end we will take summation of this particular value. In this particular case, the variance is actually 53.0 centimeter square. So this is how we calculate the variance. Based on variance, we calculate another indicator which is known as standard deviation. To calculate a standard deviation, we just take under root or square root of the variance. So basically 53.04, we calculate 53.04, which will come out to be 7.258 centimeter. So using this equation, we calculate the variance and standard deviation. Now these two indicators will tell us what is the dispersion like. So basically, if we have to calculate based on this standard deviation, we can say that 142 plus 7.258 should be given as a range of our indicator. This is something that we will discuss later. If this is normally distributed, then we can assume that about 65% of the observation would be in this particular range, 142 plus minus 7.258. So this is how we calculate variance, and this is the usability of this particular moment. Now let's talk about the third moment, which is referred as skewness. Now skewness measures the cube standard deviation. So we calculate the standard deviation based on what we did earlier, but instead of square root, we take a cube of it and divide by a cube of the standard deviation. So basically skewness tells about the symmetry of the distribution. So basically it tells us that how symmetric a distribution is around its mean. So if we have this mean here, this distribution that I have just drawn is a normal distribution which is symmetric. By symmetric, it means that the left hand side, this left hand side is exactly equal to the right hand side. So there is perfect symmetry in this particular distribution. Now this skewness tells us about one key factor which is considered as outlier. So basically what happens is that if there is perfect symmetry, if the distribution is symmetric, then there would be no outliers. Outliers are defined as the observations which found here, which are extreme values on both sides of the distribution. So it can be positive, it can be negative. and these outliers actually impact the overall mean of the distribution. So if there are a lot of values here, then the mean would be shifted here and the equation would become something like this. Now this particular equation would be considered as left skewed. For the left skewed distribution, so if there are a lot of positive values here, then it means that the mean of the distribution would be shifted to the right, and this equation will actually become something like this. This particular curve would be referred as right skewed. Now for this equation, the mean would be somewhere here, the median would be here, and the mode would be here. Mean, median and mode are three different terms we will discuss later. Median gives us the center of the distribution, and mode gives us the values which are mostly occurring. So the highest number of value would be referred as mode. On the other hand, if we have values which are mostly to the left side, then the mean would be shifted here on the right side. And in this particular case, we will have a distribution which would look like this. For this particular distribution, the mean would be shifted here, the median would be here, and the mode would be here. We will be referring this distribution at left skewed distribution. Simply putting it, if the right tail is longer, then we get a positively skewed distribution like this green one, and if there is negative skew on the left side, then it would be referred as left skewed distribution. Now these tails where we have more observations is referred as fat tails. The problem of fat tails is something that we'll just shortly discuss in the kurtosis, but basically for the fat tails phenomena, the risk that we consider in usual scenario, for the fat tail scenario, the risk becomes a little higher. So if we have fatter tail problem, then we would be facing more risk than usual. So if there is a standard deviation of risk of 10% in normal tail, for the fat tails, the risk or standard deviation may be 30%. So there is no specific rule as to be the multiple of normal distribution, but it would be significantly higher than the usual distribution, and in that particular case it becomes a little difficult to actually calculate our risk based on the normal distribution assumption. Now one critical aspect is that a normal distribution has zero skewness. A normal distribution has zero skewness, and the skewness change from 0 as we move from left to right skewed distributions. Now let's talk about the fourth moment, which is kurtosis. So the fourth standardized moment is known as kurtosis, and we calculate it by taking a power of 4 to the variance equation that we discussed earlier. So instead of a square root, we take a power of 4 to calculate the kurtosis. Now kurtosis gives us the measure of flatness of the distribution. So in the earlier slide we discussed the fat tail phenomena. Now kurtosis is actually a better measure to calculate the flatness of the distribution. The degree of kurtosis is actually measured as compared to normal distribution. So let's take this graph that I have just drawn. We have three colors. The red one is actually a normal distribution. So you will see that for this particular distribution, the value of kurtosis would be equal to 3. So for normal distribution, k is equal to 3, it means that it follows a normal distribution. we call it mesokurtic. But if we have a phenomena where the kurtosis is greater than 3, the curve would be referring as lactokurtic. And for this lactokurtic, which is shown by this blue distributions, we have fat tail issue. So basically it is comparatively taller than other distributions, and then we can see that the area that we have in the distribution is actually fatter. The tail is actually fatter than normal distribution. It means that we have more values lying in these tails. These tails basically represent extreme values. Here is the mean. So the farther you go from this mean, the extreme values would increase. So if the values are here, there isn't any problem. But if they are here, and if they are more in quantity, as is the case for this lactokurtic distribution, then the amount of risk that we will have for these distribution would significantly increase. And then if you are assuming that it to be normally distributed, we won't be able to calculate it based on this particular assumption. Now the last thing is that if the kurtosis is less than 3, we would be referring is at platykurtic, which is this green distribution. Platykurtic is pretty normal. It's more distributed, and the level of risk is more diverse, it's more dispersed, and we are not that much concerned about the distribution if it's platykurtic, but we are surely concerned about the lactokurtic where the kurtosis is more than 3. There is a phenomena of heavy tail or fat tail distribution in the financial returns, which means that if we have fatter tails, the extreme values on both positive and negative sides are on a higher side. It means that the return was 10%, but the company also booked a loss of 50% on a particular day. So these events, these outliers would impact our whole assessment. Take another very short example of mean and variance. We have a distribution given for a particular company. We have been given the dividend per share. So basically the company has to issue dividends. There is a 30% chance, a 30% probability that the dividend would be $1. There is a 40% probability that it would be $2. There is a 20% probability that it would be $3, and there is a 10% probability that it would be the dividend announced would be $4. So recalling from the earlier formula, we would be multiplying the x with the assigned probability. So we will multiply these two things and would be adding it up. So 30% to 1, 40% to 2, 20% to 3, and 10% to 4. The answer would be $2.1.